Hello, we are from Team 19 and our topic is life cycle of fracking water. This topic is of interest to us because the whole process involved with hydraulic fracturing or fracking is not widely known to the public. The process that's involved with fracking water is important to know because it might be happening in our own backyard. So fracking or hydraulic fracturing, it is a process of injecting liquid at high pressure into subterranean rocks, boreholes to attract oil and gas. Specifically, it is a well stimulation technique in which rock is fractured by a pressurized liquid. The process involves the high pressure injection of fracking liquid, primarily water containing sand or other propane suspended with the aid of thickening agents, into a well bore to create cracks in the deep rock formation through which natural gas, petroleum, and brine will flow more freely. When the hydraulic pressure is removed from the well, small grains of hydraulic fracturing proteins, either sand or aluminum oxide, holds the fractures open. So there are 6 major steps in hydraulic fracturing. First off, drill a well. So a well is drilled vertically into the ground until it reaches the permeable shale layers. Second step is pump in high pressure fracking liquid. The fracking liquid contains a mixture of water, sand, and 5 to 10 chemicals ranging in toxicity. Feed high pressure fracking liquid into the well via a pumping tank. The third is fracture the shale rock. The internal pressure of the shale rock causes the fluid to make its way back to the surface. The fourth process is prop open the fractures. This is to leave the prop ends behind in the cracks and fractures after the water has retreated. As the name implies, the prop ends prop open the shale fractures, keeping them from closing up again. The fifth step is collect the natural gas. The once trapped shale gas is now able to flow free from the shale layers because it has remained propped open by high crush fracture propanes. Last is the transfer of the natural gas. From the well, the natural gas is transferred to nearby storage tanks until it is piped to market. But what goes in a fracking fluid? So there are 3 major components that go into a fracking liquid. First off, water. Second, sand. And third, chemicals. The water used for fracking, a mixture of water, sand, and chemicals, is pumped at high pressure underground and wedges rock apart. The sand stays put in the cracks, creating pathways for oil and gas to travel towards the well. And about 40% of the water and chemicals flow back to the surface. But how much water are we talking about? So about 70 to 140 billion gallons of water used to fracture 35,000 wells in the US per year. And this is equivalent to 40 to 80 cities with 50,000 population. In other words, up to 600 Olympic-sized swimming pools of fresh water are trucked in from lakes, rivers, and streams to the fracking well. Now about sand and surrounding beds. About 300,000 to 400 million pounds of propanes used per well. Now the third component in a fracking fluid is chemicals. Now this is only about 0.5% to 2% of the total volume of fracking fluid, or up to 330 tons. Now many fracking chemicals are protected from disclosure under trade secret exemptions. Studies of fracking wastewater, however, have identified formaldehyde, acetic acids, and boric acids among hundreds of others. Now what does this chemical do? For example, acids. In fracking fluid, this is to dissolve minerals and initiate fissure in rock. Second example is sodium chloride. This is to allow delay in breakdown of the gel polymer chains. And that's some of the examples of chemicals that go into a fracking fluid.
Here we have the fracking water cycle. There's 5 steps involved, and I'll go over the first 4. The first one is water acquisition. This is when water is acquired from a source and brought to the facility. I'll talk about this a little more in the next slide. Second step is chemical mixing. Additives are put into the water to optimize fracking. So these components can be either biocides, propants, and it reduces friction and makes easier for extraction. These can also be a little toxic, which is why we have to handle them carefully. The third step is well injection. This is when high pressure water is forced into the ground, fracturing the rocks and releasing shale gas, which we talked about more later too. The fourth step is produced water handling. This is when we use fracking water and we try to clean it up, which is what the fifth step is ultimately about. So back to that first step, water acquisition, which would be water sourcing. So fresh water is becoming more expensive to obtain. And this is a huge threat to the oil and gas industry finding fresh water. Since Missouri River watershed was off limits for a while, they had to truck in water from ponds and lakes of private landowners. So this became very expensive. Also, lately, U.S. Army Corps of Engineers limit the water taken out of the watershed. So they allow some to be taken out, but not much. And as you can see in the top right here, this picture, we have, that is the Missouri watershed. So we have multiple tributaries running into the Mississippi River there. And if you look, there's Missouri River, which runs into the Bakken Shale, and then top right we have the Ohio River, which runs into the Marcellus and Utica Shale. So if these rivers are accessible to these sites and on to these wells, you can truck it. You don't really have to need to truck in the water from private ponds and pay landowners for the water. You can just pipe it right to your site, which is a lot easier and makes more sense for the companies. But so if they couldn't get all the water out from the rivers, they have to truck it in. And also they allow frac sand, which is what we talked about a little earlier, to be dredged from the rivers. So instead of U.S. Army Corps of Engineers to just dispose of it on say a side in a random spot, they can sell it to these oil and gas companies to use as frac sand at a cheap cost. Also, 20 to 30 million gallons of water per day are needed in the operations in the Bakken Shale. That's a lot of water. And in PA, it's about 4 to 8 million gallons needed for one well in a 1 week period. So, a competition between fracking operators and farmers are becoming a little issue because crops need irrigation, and say you're in Texas where there's plenty of wells and not as many, say, private or lakes. Farmers will need that water to irrigate their crops to make their revenue. And also, if there's a drought, you gotta have water for your cattle and your crops. So if these fracking operators are coming in and offering you, it's about 60 cents per barrel of water for your, say you have a 2-acre pond and they want to drain it all for the operations, which won't usually do one well, they have to get multiple ponds. You'll be out of your lake and you'll be suffering a little bit. But it also affects the availability of drinking water. So if you take water from a river upstream, everything else downstream will be hurting a little bit because it would be less water and less flow coming through. Many fracturing wells operating in the Bakken Formation in North Dakota and Montana, and also more wells in Texas, use surface ponds to store hydraulic fracturing fluids for evaporation or water used in the process. This is held here until arrangements for disposal are made. Almost 50% of the wastewater generated from hydraulic fracturing in these states is diverted and stored in these ponds. Within the past 24 months, however, Pennsylvania has completely eliminated the use of surface ponds for wastewater storage. But the future use of surface ponds is sure to become more regulated. The EPA is currently evaluating industry practices and state requirements and is considering the need for technical guidance on the design, operation, maintenance, and closure of surface ponds under RCRA, which is the Resource Conservation Recovery Act, in order to minimize potential environmental impacts.
So now I'm going to talk a little bit about deep well injection. Deep well underground injection is a disposal method used to remove fracking fluids from shale oil. This method is actually used in many regions of the United States, very primarily in Texas, North Dakota, and Montana. Some of the regions like Pennsylvania have outlawed the method because some companies have found ways to get around it on the right side though. So continuing off the last slide, companies in Pennsylvania that wish to use this method will actually transport that wastewater to Ohio. This definitely introduces some concerns about the transportation of the wastewater, as well as the effect it will have on the residents living in these areas and the roadways that are used. Some local governments in Pennsylvania require these companies to pay bonds to cover the road maintenance costs. The cost of transporting the wastewater for deep well injection is about $3 to $7 a barrel. And to remove the water off site over the entire life, 20 years, is estimated to cost $160 million. This includes trucking, water disposal, and labor costs. So the Energy Policy Act of 2005 specifically exempts fracking fluids from Safe Water Drinking Act regulations. This is also known as the Halliburton loophole. What is the Halliburton loophole? In 2005, the Bush-Cheney Energy Bill exempted natural gas drilling from the Safe Drinking Water Act. It exempts companies from disclosing the chemicals used during hydraulic fracturing. Essentially, the provision took the EPA off the job. So Section 322 is what the rules are, abide by, and it's amended to be read as follows. So Section A would say this means the subsurface emplacement of fluids by well injection, and it includes the underground injection of fluids or proping agents other than diesel fuels pursuant to hydraulic fracturing operations related to oil, gas, or geothermal production activities. So for deep well injection, there are 6 different classes of how to classify these wells under the EPA. A Class 1 well is hazardous waste, industrial non-hazardous liquids, or municipal wastewater, and there are about 680 of these wells across the United States. Class 2 wells are brines and other fluids associated with oil and natural gas production, and hydrocarbons for storage. There are around 172,000 of these throughout the United States. Class 3 is a solution of mining minerals. There are about 22,000 wells across the United States. Class 4 is hazardous or radioactive waste into or above the USDWs, and there's about 33 sites. Class 5 is all injection wells not included in classes 1 to 4. These are non-hazardous fluids into or above the USDWs, and these range from about 400,000 to 650,000 wells across the United States. And Class 6, last but not least, is a geologic sequestration of CO2, 6 to 10 commercial wells expected to come online by 2016. So now I'm going to talk a little bit more specifically about the Class 2 wells. Class 2 wells are used only for the injection of fluids associated with oil and natural gas production, as I mentioned on the previous slide. These Class 2 wells are actually subdivided into 3 different categories. These can be known as disposal wells, enhanced recovery wells, and hydrocarbon storage wells. A disposable well is during oil and gas extraction, the brines are brought up to the surface. These brines are then separated from hydrocarbons at the surface and re-injected into the same or similar underground formations for disposal. Wastewater from hydraulic fracturing activities can also be injected into these Class 2 wells. And these types of wells, disposal wells, make up about 20% of all Class 2 wells throughout the United States. Second, the enhanced recovery wells. So fluids consisting of the brine, fresh water, polymers, carbon dioxide, etc. are injected into oil-bearing formations to recover residual oil and, in limited applications, natural gas. The injected fluids will decrease the viscosity or displace small amounts of the extractable oil and gas. Oil and gas is then available for recovery. In a typical configuration, a single injection well is surrounded by multiple production wells that bring oil and gas to the surface. So the UIC program does not mention regulating these wells if they're only used for production. So that's something cool. The EPA also does not have authority to regulate hydraulic fracturing when diesel fuels are used as proping agents. And for these, enhanced recovery wells make up about 80% of all the Class 2 wells throughout the United States. And lastly, hydrocarbon storage wells, the third one. So the liquid hydrocarbons in this scenario are injected into underground formations where they are stored, generally as part of the U.S. Petroleum Strategic Reserve. There's over 100 of these throughout the United States currently operating. So with these Class 2 wells, states actually have the option of requesting primacy for Class 2 wells under sections 1422 or 1425 of the Safe Water Drinking Act. Section 1422 states that the state must meet the EPA's minimum requirements for the UIC programs. This includes well and operator requirements for construction, operation, monitoring, testing, and closure requirements. And under this section, enhanced recovery wells may either be issued by a permit or authorized by rule. And also, owners and operators must meet all the requirements, including regular testing and inspections. And the second one, section 1425, this it says that the states must demonstrate that their existing standards are effective in preventing the endangerment of the USDWs, and the programs are required to meet the requirements for permitting, inspections, monitoring, record keeping, and reporting. So next, I'm going to talk about the diesel fuels hydraulic fracturing. So in the Energy Policy Act of 2005, Congress was able to implement a broad exemption for hydraulic fracturing under the Safe Water Drinking Act. So hydraulic fracturing, except when using these diesel fuels, was exempt from the definition of underground injection. Thus, it was excluded of regulation by the UIC program. Next, in 2014, the EPA released information regarding the UIC program requirements. The agency also went on to create guidance for EPA permit writers, thus implementing UIC Class 2 requirements. These requirements and guidance from the EPA, first, they were able to explain that owners or operators obtain a UIC Class 2 permit before injecting diesel fuels for hydraulic fracturing. Second, the EPA's interpretation of the SDWA term diesel fuels for permitting purposes. So basically, it mentions what these diesel fuels actually are. Third, it described the existing UIC Class 2 program requirements for permitting underground injection of diesel fuels in hydraulic fracturing. And lastly, it provided guidance for the EPA's permit writers preparing UIC Class 2 permits for diesel fuels use in hydraulic fracturing.
The first method to treat the wastewater is wellhead wastewater treatment. The wastewater from the shale oil can contain high levels of total dissolved solids, fracturing fluid additives, total suspended solids, hardness compounds, metals, oil and gas, bacteria, and naturally occurring radioactive materials. These are all chemicals and agents that are added deep into the well to change the water chemistry, giving it a higher viscosity, allowing it to carry more sand, and improving its conductivity. All of these things allow the fracking to occur. The fracking process is essentially pushing the water down into the rock, using it to wedge the cracks in the rock open. The sand then fills in these cracks. The wastewater is created when the water from the fracking comes back up the well as flowback wastewater. Along with this wastewater, there is bacteria, minerals, radioactive materials, as well as oil and gas. Some of this wastewater can be reused to supplement fresh water in the fracturing of a new well or the refracturing of the same well. This reduces the discharge to surface ponds and minimizes underground injection of wastewater. Both of these things allow the reuse of the water, and it conserves water resources. Mobile solutions to treat wastewater at the wellhead allow companies to recycle the flowback water. This eliminates the need to store it in surface ponds or needing to transport it away to a deep well injection location. The recycled wastewater is specifically treated for the geology of a specified well site. The mobile solutions do not provide continuous processing, however, and it would require about 20 years of processing after the fracking to get rid of it. The next method to treat the water is centralized water management. This reuses as much of the wastewater as possible, which makes it a solution for long-term efficiency of managing water sourcing and wastewater treatment. The centralized treatment facilities deal with both the flowback wastewater and the produced wastewater, and it has pipelines that connect all of the wellheads with the treatment plant. The wastewater going into the plant is recognized as being from a specific well. The water is then given a purpose and it's processed for the specific purpose and then sent to the targeted well site that it was treated for. Centralized wastewater treatment facilities have multiple processes. The primary three-phase separation is the first one. It removes natural gas, floating gel, oil, sand, and suspended solids. The next is the secondary separation, which uses dissolved air or gas flotation to remove contaminants. These contaminants include polymers, oils, and suspended solids. At this point, bactericide is also added to control the growth of the bacteria. Next is the removal of metals by precipitation, as well as the removal of salts by reverse osmosis. Finally, sludge management occurs for dewatering the collected solids. Centralized plants can be used with alternative water sources to supplement the fresh water that is used for the fracking. These alternative sources include water from abandoned mines, stormwater control basins, and power plant cooling water. This adheres to the mandates from Pennsylvania's SRBC and its Department of Environmental Protection. They work to increase the reuse of water for fracking and also increase the use of alternative water sources such as treated wastewater and acidic mine drainage.
The earth acts as a somewhat porous medium, which allows water to flow through it and diffuse through the ground naturally. Underground water sources have been used by humans for many thousands of years, and still today in a lot of private residential homes in rural areas, homeowners will drill their own wells and get their water supply from there. Natural gas wells or fracking wells that are being drilled, the vertical shaft, which the water is being pumped down through, will be encased. But the entirety of the ground that you're spraying the water into, fracturing the rock, is not. Not all of the water will be captured, and some may diffuse away. To the extent at which it diffuses, the distance it travels, the distance that the contaminants flow along with the water is incredibly difficult to model, because modeling the flow of fluids is challenging to begin with. But then you're adding it in a porous medium where it's hard to know and define the boundary conditions accurately. And you also want to model how the contaminants within the fracking fluid would flow through ground supply water. There's a lot to be considered. For instance, the depth of the well. California, around half of them are on the order of 2,000 meters deep, which is fairly shallow, which makes this a still open debate and very difficult to understand exactly what will happen to the fluids. Methane is the foremost component of natural gas, and a scientific study has discovered that it was recently found in concentrations above the action level for hazard mitigation as defined by the U.S. Department of Interior. These were taken by multiple sites around Pennsylvania natural gas fracking wells that were both active and inactive. An important thing to note is that the x-axis, which measures displacement, is in unit meters, and all the way out is more or less at about 5,000 meters. So the vertical displacement, the displacement from the well is very small to begin with. It should also be noted that some of the wells that do have high levels of methane are very near the well itself. And some of the locations very near the well that are active also have very low concentrations of methane. This suggests that the wells that have low methane in the surrounding water supply must have a better job of encasing and preventing the methane from leaking out in any manner than some of the other wells which locally have methane levels that are considered above safe. It's hard to capture and clean 100% of the water that is used in fracking. Of some of the contaminated water that's sprayed in to fracture the rock, not all of it comes back to the surface, gets recycled, gets cleaned, filtered, or reused in some way. Inevitably, some is going to escape. Much of it will reside in the earth, and some may diffuse further. The greatest concern with fracking water is that it inevitably contaminates in local drinking supplies. Many residents rely on their own private pumps, which drill into the earth and use the water pulled out. Should fracking water contaminate their well water, then that is their livelihood that is being contaminated. So it is of the utmost importance that any fracking well that is inevitably drilled is maintained and contained to the most of their ability. In Northeast Pennsylvania, multiple lines of evidence from the EPA concluded that 9 of 36 drinking water wells have been impacted by stray methane, ethane gas associated with near hydraulic fracturing activities. In southwestern PA, there was an increase in chloride in groundwater near the impoundment sites which contained the fracking wastewaters. Due to the briny nature of the wastewaters, they can deposit salt or chlorine behind. In conclusion, fracking's effects on the water supply are very uncertain and unknown in a lot of regards because how things will diffuse, how things will spread, and a lot of health hazards associated with it are not completely understood. However, it has been shown that a lot of wells can be safely created, that wastewater can be contained and recycled. It has also been shown that in instances where there is leakage of containment, it can lead to instances that could cause health concerns. But with America greatly being in need of energy, I think that there is a outweighing of any cons relative to the pros, that it is much better that we do frack and extract the fuel that we can to help power our society. Natural gas is extremely advantageous for America to use as an energy supply because it can be toggled on and off quickly through natural gas turbines. That many power plants, such as coal and nuclear, are baseload power plants and will put out a large constant amount of power. They are inadequate at switching their production to meet rapid fluctuations in demand. Because of this, natural gas burnt in small turbines is incredibly effective because it can be controlled how much is being dispatched. Ideally, fracking natural gas will be an energy source that is inevitably a stepping stone towards something cleaner, towards more solar, more wind, more renewable. But in order to meet the current energy demand that we have as of now, it is important for America to frack for natural gas as cleanly and effectively as possible. We need to make sure that we don't let briny deposits wind up polluting aquifers or natural water supplies, and realize that accidents can and do happen. And I think we need to take the utmost care that we can so that we can prevent the gas itself from getting into water where people's own private wells that run for their house. It's paramount that we take care of the earth when we take our resources from it. Finally, in review of the water life cycle of fracking water, first, water is sources. It may be taken from a river, it may be taken from a pond or lake, but clean water is required for the fracking process. And this increase in demand that comes from fracking will put a demand strain on the water supply. No matter where the source comes from, this is still going to affect the ecosystem by pulling water from it. Once the water has been acquired, chemicals will be mixed into it to adjust its physical properties, making it more ideal for fracking. There will be additives to lower its viscosity so it flows through the pipes better. There will be additives of sand to fit in between the cracks made in the rock, helping them fracture. Once these additives have been put into it, the actual fracking process can be done. Once the wastewater is generated, there are multiple different ways that it will be processed. Deep well injection, which must abide by various federal regulations, is prohibited in some places such as Pennsylvania, but commonplace in others. Another disposable method is you may have a shallow pond where the water will evaporate and the contaminants will remain behind and then later be processed. The water handling and disposal, reuse of the water at the facility will typically be done with either a wellhead facility, which is more short-term, set up at the wellhead to recycle, process, and clean the water as much as possible, or a centralized facility where you have one facility that may treat multiple wellheads centralized around them, and it processes the whole treatment facility, kind of bringing everything together into one. So ultimately, how water is handled, how it is treated and processed through this entire life cycle is one of the most important things that the company mining for the gas can go through. The water has to be cleaned so any toxins and chemicals are removed and not added to the earth. Any diffusion from the well site needs to be mitigated to every extent that's possible. And ideally, the best thing to do is try to reuse as much of the fracking water as you can, to at least have a wellhead on site where you clean and reuse some amount of the fracking facility, which is more of a short-term solution, or long-term you have a centralized water treatment facility at the well site where you clean and process. Reusing the water will help lessen any burden on natural resources and processing and containing any contaminants so as little effect to the environment is done as possible, so that there isn't any harm to the ecosystem, all because we needed to meet our energy demand. In conclusion, we are greatly in need of energy, and natural gas is a phenomenal supply. Fracking has been shown that it can be done very cleanly. However, it needs to be done as carefully as possible to avoid any contamination or any leakage into the surrounding areas to prevent hurting the surrounding ecosystems. Natural gas is a very important energy supply that will help power America. It is very important that we acquire this. However, it is equally important and that we acquire the gas in such a way that we don't hurt the earth.